within Multiscale Designer. The general key features within in that release are we added the support for let's say the general gradient scalar field homogenization back into the tool, adding thermal conductivity and diffusivity. We added a more detailed review of the homogenization results, focusing on the unit cell results. We added the last missing unit cells, core unit cells, and some small enhancements on the user-defined unit cells. And one of let's say the major missing features is this general inverse analysis, which enables the inverse characterization of any of any within any material template, let's say allowing the full freedom to the user. General goal of that release is, I'm kind of optimistic that I'm closing the gaps in the GUI process, which were still open concerning to the last 2024.1, or what we internally call the classic version. So we added all the needed features. So there shouldn't be any feature gaps anymore concerning the last classic version within the GUI workflow. Now let's have a look at what's implemented. First is this universal framework, any scalar gradient, gradient scala in input in let's say homogenization is again available from the GUI. In the back end, it was also available. We only needed to activate it in the GUI. Major applications we see right now is the heat conduction with thermal conductivity, electric conduction, electric permittivity, and for diffusion processes with diffusivity. The nice thing of that framework is, however we call the input data, the physics and the math framework is the same. So even if it's called thermal conductivity, if you put in the electric permittivity, you will get the proper electric permittivity of a unit cell. Output of that analysis is one forward run, and you will get the homogenized material properties of a microstructures for composite and lattice materials concerning these kind of physics. The implementation, which was the philosophy with the entire new GUI, implement a similar feature, but implement it better. So what we did, we split the material input into the physical parameters, linear elastic and non-linear mechanical parameters. And within the physical parameters, now you can define the thermal conductivity and the diffusivity. Depending on the material law, it can be isotropic, transisotropic, fully 3D orthotropic, and all this input is supported. If these values are put to 0, we don't run the homogenization of the thermal conductivity. If these values are defined, let's say with a value higher than 0, we run the homogenization in the background. Perfectly matching, let's say, to that feature, we also added, let's say, a third tab in the elastic result. So we have a job definition, we have a virtual test result summary, and now we added again let's say the full summary of all results of a homogenization on unit cell level, starting from the density, the thermal conductivity, diagonal terms, and the full matrix. Same for the diffusivity. We have and CTEs and the 3D orthotropic engineering constant and the full anisotropic stiffness matrix. All that can be easily exported into CSV for further usage. As you can see, you can define the thermal conductivity. Let's put that value to 0.1 for the matrix and allow a bit of more thermal conductivity, for example, from fiber in one direction and less in the second direction. These values don't necessarily need to make sense. And now, if I go into the forward linear analysis, and I run the forward linear analysis, on top of this, let's say on top of a virtual test result review, now we have the summarized review here of all these results. You can export this as CSV. For example, this would be if you would hook that to OptiStruct, that would be a four card. In Abacus, it would be again another material input, and everything can be reviewed here. One of the other remaining issues we needed to add was the core unit cell support. It didn't make it to 2025.0, so now we added it to 2025.1. So we put back this high density foam unit cell and the honeycomb unit cell geometry. These are available if you go to File, New. I switch to the core unit cell, and here you can choose between foam, honeycomb hex, honeycomb ox. Let's take the hex one. I will choose whichever material. Polymer is fine. You can either input the geometric data, cell size or foil thickness, or the density, and we will calculate the geometric parameters for you. Let's go for 0.05. We can assign any material. Let me talk a bit more in detail about the different inverse characterization methods we implemented. Till version 2025.0, we had two different inverse characterization methods. Inverse means you have a set of test data, a specific set of test data, and you want to fit your micromechanic parameters to fit, let's say, to find the closest fit to your test data. We started with fixed schemes for the most used materials. These are continuous hexagonal with hexagonal square unit cells, or discontinuous. Since these materials have a different test scheme, different characteristics, different influences, for the, let's say, for the continuous, we support this hard-coded split of linear and non-linear inverse characterization. So first we need to do the linear. Only if that's done, that makes sense to go to the long linear, and it's fixed to a specific test scheme. That means longitudinal tension, longitudinal compression, transverse tension, transverse compression, and or in plane shear results. All of that was a fixed scheme designed for an easy use of an inverse fit of continuous. We had something similar for the discontinuous, which is this combined inverse. Here we optimize the geometric parameters of a unit cell, the elastic and inelastic parameters in one shot, since for that material and with these characteristics, it's proved to be more useful. What we were missing was some kind of general inverse characterization approach for any other material. That's added now. So any other material template besides these two supports this general inverse characterization. What does general inverse mean? You as a user have a full freedom. So you can choose, as you can see here on the right-hand side, every parameter of a model to be changed to fit your measurement data. It can be geometric parameters of a unit cell and any other material parameter. On the left-hand side, the input. So if you only type in the modulus, you would only optimize the elastic regime. If you add the stress-strain curve, we also fit to the nonlinear inelastic regime of your material. Now it's your choice which materials do you want to change, which parameters should be optimized, and you can add equality constraints forcing two values to be the same during the inverse optimization. Very useful, for example, if you want to optimize the tensile modulus to also change the compression modulus and link them to be the same. Why? Because if I change the tensile modulus too much, it can happen that the material model gets unstable with a couple of parameter sets. To avoid that, you can enforce these two values to be the same. Could be one example. That setup provides the full freedom of doing geometric, elastic, inelastic optimization versus test data. In one shot, in one shot, you can split that into only elastic first and then inelastic, and provides you the full freedom to define your inverse process. For sure, you need high understanding and which parameters should be changed are beneficial to come up with a useful setup and, let's say, to get to good results. I prepared one example, which I will show in a second, let's say to also explain a bit how these constraints can be used. Here I took this toe-based plane weave model. I have the warp and the weft toe with some geometric parameters, and the toe is a high fiber volume fraction unidirectional material, 80–85% fiber volume fraction. And in nature, the toe will be trans-isotropic, which can be seen here, that we have a modulus in one direction, and in 2 and 3 direction, it should be the same. Same accounts for the let's say also for the G12 and G13 result. So now, how could I set up an inverse toe? Let's assume it's only elastic. So to fit to our test data and keep these characteristics of a material. Both toes are the same, and I need a trans-isotropic. I want a trans-isotropic behavior of the toe. So elastic means we only type the modulus here. We provide no stress strain curve. I have 8 design variables in my case. I have the E1, G12, G13, and E1 compression for each toe. 2 times 4 makes 8. Both toes are the same, so I need to put these 5 constraints, which are linked by the ID of a variable. So E1 of toe X always needs to be the same like E1 of toe Y, the same for the E1 in compression. And the second constraint I defined was that the shear modulus in 1–2 direction and 1–3 direction needs to be the same, and needs to be the same value for both toes. All these together sets up to 5 equality constraints, which are defined here. Number 5, and when you type the IDs here, the IDs can be taken from the list. Taking that, in this case, I'm fitting my expected value with a simulated value with let's say, with a very high accuracy. And you can see the optimized parameter set down here. So the tensile modulus E1, which is exactly the same between both toes. The shear modulus G12 and G13, which is exactly the same due to the quality constraint. And that's the setup. Let me quickly show that thing. So here, that's the unit cell. And if we go to the inverse setup, I have my 3 load cases. I have a longitudinal tension with a mean modulus, longitudinal compression with a bit lower modulus, in plane shear, that's a 45 minus 45 tension, and that's the slope of a stress strain, normal stress, normal strain curve. On the right-hand side, sorry, I selected the active variables out of a full list, so I want to change the tensile modulus. So I can see it better. Tensile modulus of tau X. I want to change shear modulus G12 and G13. I want to change the compression modulus, and the same for the second toe. And you can see the IDs which are linked here. And by hitting run, that thing will run and provide exactly these results. And that's the inverse general fit. I tried it with a lot of many variants with user-defined unit sets and anything, and works fast and stable. The major challenge is you, as a user, need to define your setup, and it's not always straightforward to find the best setup right away. Because we always need to keep in mind that we, without noticing, you put in the background some constraints to keep the material law stable and stuff like that, which might sometimes leads to some initial unexpected results. And that's basically, that's it from the, say, from the release 2025.0 multiscale. That's the key new enhancements.